So good evening to one and all. Yesterday we have gone through the classification of transducers. So in that we are having several types of classification based on the source of input available, whether it is self-generating type or non-self-generating type. So active and passive type of transducers, primary, secondary transducers, based on the number of transducers what we are going to use based on the application. Then transducer and inverse transducer. So up to first and second we have gone through. Okay. Now we are going to move to the analog and digital transducers, right? So these are all the things what we have covered yesterday. So active transducer, passive transducer. So their classifications: thermoelectric transducers, piezoelectric transducers, photovoltaic transducers. These are all comes under active transducer, where it doesn't require any external supply, nothing but self-generating type. The passive transducer required external source. Without that external source, it is not possible to convert that one form of input into another form of output, right? So there are various classification: variable resistance, variable reactance, optoelectronic, etc. So in that, today we are going to discuss about the passive transducers. So these, yesterday we have gone through about the LVDT. This is one of the best application. Then coming to the analog and digital transducers. So analog and digital means, so what kind of output? So here input will be there, a transducer will be there, and output can be produced. So here there are n number of sources are available in the nature, and these n number of sources are converting into, let us say, as we belongs to electrical, so electrical outputs are going to be obtained. So we can treat this as electrical transducers. So here what kind of output it is going to produce, whether it is going to produce analog or it is going to produce digital. So based on the analog output or digital output, we can have the classification, because nowadays digital transmission of digital data is very, very essential and very easy. So that's why most of the cases they are preferring digital output. Even we can observe one thing, in the strain gauge application, whenever the weights we are going to add in the plate, okay, the what you can say, the strain whatever it is measured, okay, that will be converted in terms of voltage or in terms of micro strain, and it is directly displaying on a panel. So where we are going to get a digital value. So digital value in the sense numerical values. So directly we can note down these values. So analog means we can have in terms of a waveform or like this. So digital output as well as analog output. So depending upon the type, so whether it may produce the analog output or it may produce digital outputs. So on the basis of this nature of output signal, it may be classified as analog as well as digital transducer. So analog transducer converts input signal into output signal, which is a continuous function of time. So here it is a continuous function of time, nothing but with respect to time, certain amount of voltages or certain amount of some of the quantities are being changed. So the best examples are thermistors, strain gauges, LVDT, thermocouples, etc. Because with respect to time, as the temperature gets increased, the the value of resistance may change, whether increasing or decreasing, right? Even in the strain gauge applications, LVDT. Yesterday we have gone through the LVDT concept in the previous topic. Okay, with respect to time, the waveforms are there. These waveforms are increasing or decreasing. So that and all we are measured with respect to time. And coming to the digital, so it converts the input signal into output signal in the form of pulses or discrete output. Discrete output means, let us say, I am going to draw a sinusoidal signal, let us say. This is a sinusoidal signal. So this sinusoidal signal can be discretely maintained, nothing but we are going to just increasing like this. See, observe how it will be. So it is also seems to be sinusoidal, but it is discrete in nature. So a stepped waveform like this. Okay, so from here we can have, or else we can draw this as like this. So a sinusoidal signal magnitudes are increasing like this, like this, like this. See, so just observe these two waveforms, this waveform and this waveform, and this is the input waveform what we can give. So the data what we have obtained will be represented either in the form of pulses or either in the form of discrete output. So this comes under discrete and this comes under digital or in the form of pulses. So pulses will be just like a spikes. So the height of the pulses may change according to the nature of the input signal. So anyhow, we are going to transmit or we are going to convert the data from analog to digital. So analog to digital converters ADC and digital to analog converters DAC can be used. Even analog to digital converter is also treated as a transducer because it is going to convert analog data into digital data. Similarly, digital to analog converters also. Okay, so these kind of digital transducer are becoming more and more popular in nowadays because of advantages of the digital measuring instrument. So wherever we are going to measure certain quantities, everywhere we are using digital meters, digital instruments, digital voltmeters, digital multimeters, like the way. So because of there are several advantages what we can have in case of digital instruments. So at the same time, we can have some advantage. We can transmit these data over a long distance without having much distortion. Okay, so that is also one thing. That is one of the advantage. And there is no phase shift, there is no variation of amplitude, etc., etc. Right? So sometimes analog transducer combined with ADC, nothing but analog to digital converter, so that the digital data can be transmitted accordingly. Right. So that is about analog to digital converters. Now coming to the transducers and inverse transducer. This is also one type of classification. This is also one type of classification. In case of, okay, simply we can say transducer is a device which converts one form of energy into another form of energy. Inverse transducer, let us say A is a kind of input source. The transducer will be there and output will be B. So if you are converting A to B, so A to B by means of one transducer, transducer 1, T1, let us say. And if you are converting B to A, nothing but inverse operation. So for that, this transducer is not going to be used because, for example, let us say this is what I can say, displacement, and this is voltage. Okay, displacement is converted into voltage by means of, let us say, LVDT. But LVDT will not convert voltage into displacement, isn't it? So A to B, A is displacement and B is voltage. For that, we are using LVDT. Now, voltage is going to be converted, nothing but B is going to be converted into A. So for that, LVDT is not going to be used. So here we are going to use an inverse transducer. Okay, so transducer is converting one form A into B, and the inverse transducer converts B into A. That is known as the case. Okay. So inverse transducer device that converts an electrical quantity into non-electrical, because as we are dealing with electrical transducers. So electrical transducer means non-electrical quantities are converting into electrical quantities. So inverse transducer means electrical quantities are being converted into non-electrical quantities. That is only the difference what we can have. Okay. So there is one example, thermocouple. Thermocouple, we are applying certain amount of heat. So where of course heat is a we are going to get that heat through by heating the elements. Okay. So that heat can be converted into voltage. Nothing but in the thermocouple we can have variation in the resistance. Okay, right, as well as increasing or decreasing linearly or non-linearly, etc., etc. So these are all the cases what we can have, right? So piezoelectric crystals also can be used for translational or angular moving coils. So these are all comes under inverse transducers. Now, on the basis of the principle of transduction principle used, so here we can have several classifications like resistive transducers, inductive transducer, capacitive transducers. And again, there are several types of resistive transducers are there, inductive transducers as well as capacitive transducer. So based on the principle. So principle means, so what is the input A and what is the output B. So here there is certain process is taking place. That process is nothing but principle. Yes, voltage is okay. Solar sun energy is converting into voltage. So that is the principle. So photo diode or nothing but what we say photovoltaic cell. Photovoltaic cell is a device which converts photo energy into electrical energy. Strain gauge. Strain gauge is a device which converts the strain into change in voltage or change in resistance. So thermocouple. So the device which is used to convert the temperature into voltage like that. So we are going to say certain principle. So for every application or for every transducer, there must be having one principle behind that. That principle, based on that principle, we can have several classifications. Okay, so here we are showing only resistive, inductive, and capacitive only. Only three we are showing, but we are having n number of conversions are there. So all these conversions will be there in the form of or transduction principle. Okay, now apart from this transduction, they are also classified based on applications, based on the energy conversions, and based on the output signal also. Okay, so classification is not only based on so far what we said, along with based on applications also we can classify based on the method of energy conversion. So what is the method we are using to convert the energy from one form to another form? Based on that form also we can have different classifications. So based on the nature of output, okay, there are certain transducers which are producing certain outputs. So all comes under one category. Okay, let us say the output is voltage. The output is voltage. So whatever the transducers which are producing voltages can be treated as one group like that also. Okay, so on the principle we can have several classifications, right? Now we can have an observation here. So few of the things we are going to discuss in this class, right? Okay, so capacitive. So the total the transducers are classified for capacitive transduction, nothing but how the capacitance is going to be changed. Electromagnetic induction, inductive transduction, piezoelectric, photovoltaic, and photoconductor. So these are few things what we are going to discuss in our syllabus, right? Now we'll go in detail each and every one. So capacitive transducer. So capacitive transducers are measured and converted from change in capacitance. So the output will be change of capacitance. So for that, what are the inputs we are going to give? Okay. So normally we know about a capacitor which consisting of two parallel plates. And these two parallel plates are conducting materials and are separated by an electrical insulating material that we are calling as a dielectric material. Okay. So by changing the dielectric material, we can change the capacitance value. By changing the area of parallel plates, we can change the capacitance value. By changing the distance between the two parallel plates also, we can change the capacitance of the transducer, right? So here the even the plates are flattened or rolled also we can use. It may not, we cannot say the two parallel plates should be there. The two parallel plates need not to be as a plate. Okay, it may be rolled or flattened also can be accepted. Now just observe, there are two lines are there. So between the two lines there is certain distance is there. Okay, and the two parallel plates are having certain cross section area capital A. Okay, let us say this is plate 1 and this is plate 2. These two plates are parallel. These two plates are parallel just like this, right? Now we can change the dielectric. Okay, we can observe this is plate 1 and this is plate 2 and this is the dielectric. So we can change the dielectric so that we can change the value of capacitance. Okay, so we can have the formula epsilon A by D. Epsilon A by D. So we can have the formula. So with that formula, we can change. So we can change either cross-sectional area, we can change the distance between the two parallel plates, we can change the epsilon, nothing but dielectric strength. So by changing any of these three, we can change the capacitance of the capacitor, right? We can have the formula also. So C equal to epsilon naught epsilon or A by D. So what is epsilon naught? Is nothing but absolute permittivity of vacuum. So in the vacuum, what is the dielectric strength, like that we can say? Epsilon or relative permittivity. So with respect to vacuum, so how much amount of relative permittivity will be there? So what about the air? What about the oil? What about the gases? What about some other liquids? What about some other gases? Okay, so in our laboratory, we can see one experiment, dielectric strength measurement, right? So in the dielectric measurement of dielectric strength, there are two electrodes are there. The two electrodes are separated by certain distance. Okay, these two electrodes are immersed in the oil. That oil is transformer oil. We are going to measure the dielectric strength of that particular oil, and we are going to apply certain voltage by means of an automated or motorized controlled input, so that the voltage will be increased up to kilovolts of range. At certain extent, certain voltage levels, there is arc is going to be formed between the two electrodes. The oil, whatever we have placed in that, is going to be quench that arc, nothing but put off that arc. Okay, so up to what extent it is going to be get withstand. So if you increase the distance between the two parallel plates, automatically we need to apply more amount of voltage to get the arc. If they are very much closer, so even less amount of voltage is sufficient to produce the arc, right? So that distance plays a vital role. By changing that distance between the two parallel plates, okay, the capacitance will change. By changing the permittivity, nothing but epsilon values, so that we can change. By changing the overlapping area, nothing but cross-sectional area. Yesterday I said, if there are two parallel plates are there, the two parallel plates, in the two parallel plates, one parallel plate is moving, and one parallel plate is fixed. Okay, if we are moving, just observe, this is only the area where we can have the effective area, and the area which is at the top or the area which is at the bottom are not connected anywhere. So this is not considered as effective area. Okay, when these two are parallel, then we can produce or we can have more, as A is high, nothing but effective area is increased, then automatically the capacitance value will increase. If area is decreased, then automatically area will decrease, so that the capacitance will decrease. If you increase the distance, so capacitance is inversely proportional to distance. So if you increase the distance, capacitance will automatically decrease, right? Okay, now here we are going up, just observe the physical parameters here. Forget about this dielectric constant or dielectric material, because this deals with a proper material, a particular material. Okay, here area and distance between the parallel plates are comes under physical parameters. Why I am saying is, these two parallel plates are placed whenever we are moving in the linear direction. Observe, whenever we are moving the plate in the linear direction, nothing but one plate is moved in the linear manner. Okay, in the two parallel plates, one plate. Okay, let us say this is the plate what we are moving like this. So this is the first plate and this is the second plate. Okay, now observe, this is only the effective area. Okay, so here we are moving in the linear direction. So where linear direction or linear displacement is a physical parameter, so a physical input. So linearly we are moving one plate. So that linear motion is going to be converted into change in capacitance. Just observe. So displacement, now we can have displacement is converted into change in capacitance. Change in C value is going to be changed because as one parallel in the parallel plate, one plate is fixed. Another plate we are moving towards upward side or towards downward direction. We are changing linear motion. Linear motion. So this linear motion is a physical parameter. We are changing, we are moving, movement. Okay, so that effective area will change. According to that, C will change. Right? Then second one, the distance between the two parallel plates. Now this is actual capacitor having capacitance of C. Now we are increasing the distance between the two plates. Distance has increased. Here the distance is very less. Here D1, D2. As D1 is less than D2, the capacitance 1 in first case and capacitance 2 in second case. So C2 will be less than C1. So here also we are going to move the plate in this direction. Okay, anyhow, plate A and plate B. Plate A is fixed, even first case or second case. Plate B is moving in vertical direction, sorry, horizontal direction. Earlier we have moved in the vertical direction to change the effective area. In order to change the distance between the two parallel plates, we are going to move one plate, nothing but plate B, in the horizontal direction. Okay, plate B is moving in this direction. So here distance will change. Here area will change. Is it clear? We are making two variations. Displacement. One is in vertical direction, one is in horizontal direction. If you move one plate in the capacitor in the vertical direction, area of cross section will change. Effective area of cross section will change. Okay. If you move that one plate in the horizontal direction, distance between the two parallel plates will change. So here we need to observe that displacement is the factor is going to converted as change in capacitance. Displacement is converted into change in capacitance. So this is about the capacitive transducer. Now simply we can say, we know about Faraday's laws of electromagnetic induction. So whenever a current carrying conductor placed in a magnetic field, it influences or it is going to produce certain amount of voltage. So here we are moving the magnet in either the direction. See, the magnet is moving into the coil and out of the coil. So because of moving, so there is no physical contact between the magnet as well as the coil. So induction is going to be takes place. So the measurement is nothing but the magnetic flux is going to be changed. Okay, the magnetic flux is going to link with the coil or will not link with the coil. If the magnet is moved into the coil, then more amount of flux will be produced. Okay, if it is coming out of the coil, then flux will be less. So that automatically voltage will decrease. You can observe whenever the magnet is moving towards the left side, we can observe the voltmeter is decreasing in this direction. If the magnet is moving in the left direction, the voltage is moving. The magnet is moving in inside the direction, the voltage is increasing. So this is simple electromagnetic induction. So Faraday's laws of electromagnetic induction principle, this is the one. Right? Here, this comes under self-generating also, because just we have placed the magnet. It doesn't require any additional source of supply. Okay, so it also comes under active transducer, right? So the same things what we can have here. Earlier we have made that voltage. Now we can observe in terms of current. So the magnet is going to be placed in either the directions, either vertical or horizontal. That we can observe. We can connect another coil. We can place that coil. Just observe here the second figure. Okay, here this is the magnet. Okay, it consisting of certain flux. Okay, this is another coil. So whenever the magnet is moving either this direction, either vertically, inside and outside the coils. Okay, Now here, instead of using a magnet, we can go for a electromagnet. What is the difference between magnet and electromagnet? So magnet is permanent. So nothing but permanent magnets. So available in nature. Electromagnet is a coil is going to be gets energized with the help of a battery. So we can call it as an electromagnet. We can call it as a electromagnet. Due to aging, the permanent magnetism may lose, but electromagnet will never lose its property, because unless until we are going to change the battery, right? So how the current is going to be gets induced, we can observe the various diagrams. So here they have placed one switch. Okay, a battery is connected to the another electromagnet, and here it is connected to the voltmeter. So as it is moving in either direction, so automatically the amount of voltage will change accordingly. A similar pictures what we can have here. Okay, the same thing it is explained with the when the magnet is under rest condition, when the magnet is under moving condition. So movement is happening in either the direction, either upward to downward or downward to upward, like that, right? So these two figures deals with the magnets, and these two figures deals with the electromagnets. The principal operation both are same. There is nothing different. Now coming to the inductive transducer. So the inductive transaction, the measurement is converted to change in self-inductance or of a coil. So whenever you are calling about the inductance L, we can have self-inductance and we can have mutual inductance also, right? Both the things we are going to discuss in this concept. So the change, whatever the input we are giving, the output will be change in inductance of the coil. So it is achieved by displacing the core of the coil that is attached to the magnetic sensing element. Just observe this, the diagram. In the inductive transducer, so here we are using a coil. Okay, a coil is connected to the output unit so that we can measure how much amount of inductance will be there. Now we are using a core. Okay, the core can be displaced in either the direction. So it is movable. It is movable in the vertical direction. Okay, so that there will be certain air gap between these 2 points. There is a air gap between these 2 points. So here we can have a, a clear vertical displacement, right? So that the air gap here and the air gap here, in these 2 places, the air gap is maintained constant. So that even the reluctance also will change as of the air gap changes. So that the inductance will change. Now coming to the second diagram, here we have made 2 coils, coil 1 and coil 2, coil A and coil B. So and here these we have placed on a pivot. Pivot means just like this. Okay, the core has placed like this. Now we just like a seesaw. What you can say? In the park, you can find a seesaw machine, a seesaw playing tool. Okay, one person will sit at one side and another child will sit at another side. So both are making swinging. Okay, we can call it as a seesaw. So just like that here. So this is the common point. We can call it as a pivot. So this distance and this distance. So once it will move just like this. Okay, another time it will move just like this. So just like this, like this, like this, like this. So if this is the, okay, if I connect as pivot like this, I can move in this direction or I can move in this direction. So angular displacement you can observe here. Earlier, the displacement is in the vertical direction. So either increasing of distance or decreasing the distance. But whereas here, we can change these positions are like this. Okay, so that what will happen? The distance between the air gap at the 2 sides will change in different natures. So at one time, it will be less at one side. At the same time, the opposite side, the air gap will be more, so that the reluctance will change. According to that, the inductance will change. Okay, so just like it is swinging like this. It is swinging like this on the pivot. If it is moving like this, then automatically this side air gap will be reduced. If it moves like this, the air gap will be reduced this side and air gap will be increased this side. So this is how it can be moved like this. So here this movement is taking place in the, we can call it as a rotational displacement. So earlier it is linear, now it is rotational, right? And there is another portion is there. There is another diagram. Okay, so we can call this as bellows. So here these are nothing but how we can say just like a pumping positions. So we can apply certain amount of pressure. మీరు కొలిమి చూసారా, కొలిమి furnace. So in order to melt the metals, okay, in order to melt the metals in the furnace, they will keep the metal and from one side they start pushing the air. Okay, so with the help of these leather bellows, we can call these as bellow. Okay, with this the air is going to be get inlet into the furnace, so that whatever the metal kept in the bowl will be melted and it can be used for different shapes. So here what we are going to use, even our foot pump. Okay, in our laboratory there is Borden tube is there. We are applying the pressure through the foot pump. There we have used the pipe. We have used the pipe instead of, we are using just like these bellows, or simply we can say balloon. How it will be? If you start blowing the air, it will just increase its, what you can say, its size. Okay, like that continuously we can increase and decrease the pressure values. According to that, what will happen? These will compress or expand. These will compress or expand. Okay, just I will try to show the image. Yeah. Yeah, see this diagram. You can observe. So this is the furnace. This is the furnace what we can have. So on the furnace at one side, the person is going to handling these two bellows. So they are going to be applying like this. I mean, they are going to send the air into these bellows, so that it's nothing but it's made up of with the leather. Okay, so in order to avoid the leakages, right? So this is an example for bellows, right? There are few more images are there. So where we can have applying from here this end, so that the air will be entered into the furnace, so that we'll get good flame. Okay, this is called bellows. So the same that we have placed at these positions. Okay, so whenever you are applying pressure, this will move in either the direction. So the direction will be either in this side or this side. So because we are moving that bellows in vertical direction, so that what will happen? There is a spring connected here. There is a spring connected here. Whenever the spring is applied with certain force, then what will happen? It will compress or expand. It will compress or expand. By the time, here we can have coils. Here we can have coils. So whenever we are applying certain amount of pressure, so that the position of contact terminal will change, so that the number of terminals will change automatically, the amount of inductance will change. So whenever you are calculating the inductance value, N is the number of turns which will plays a vital role. L is proportional to N. If N increases, L value increases. Okay, if you change the pressure value, so now pressure is the inlet, pressure is the input. Now pressure is converting into displacement. The displacement is connected to the coil positions, nothing but the contact terminals, so that the inductance value will change. So pressure is converted into displacement. Again, displacement is converted into change in inductance. Okay, so this is primary transducer. This is secondary transducer. You can observe in that way also. There are two transducers are there, right? Pressure to displacement, first transducer. Displacement to inductance, second transducer. By changing the number of turns, we can change this. Okay, we need displacement as input to change the inductance, right? Now coming to the piezoelectric, as we have already discussed about in case of active transducers. Once again, just briefly, I will say it is just like a sandwich. Okay, at this is the crystal material which is placed between the two ends. So one end is fixed or another end is okay. Whenever you are applying certain amount of force from both the sides, so it is influenced with certain pressure. So whenever it is going to be applied with certain pressure, it will change its dimensions. As the dimension changes, it is going to produce the voltage. Okay, it is going to produce the voltage. So this is comes under active transducer also, because in order to convert these physical changes, there is no requirement of additional electrical supply. So piezoelectric crystals are going to be generate the voltage directly whenever it is mechanically stressed by applying certain weight or something, right? So photovoltaic transaction. So this also we have gone through briefly. And here, whenever the light ray are falling on the photovoltaic cell, there are n-type layer and p-type layers will be there. So electron transfer will takes place from n-type to p-type. So the electrons will move from n to p, so that the electrons will circulate in the a closed loop, so that where the load is going to be gets connected, right? So the voltage is going to be generated, and it is going to be when the junction between the two dissimilar materials. Here also n-type silicon, p-type silicon. These two are two dissimilar materials. Whenever the photo input is going to be applied on this, the voltage is going to be gets generated. So just observe, the solar sun rays are falling on the n-type, and the electrons are moving from n to p or p to n, so that there is a flow of electrons through this load, so that we are going to produce certain amount of voltage. This comes under photovoltaic transduction. So this is and one more animation where we can have a p-type semiconductor and n-type semiconductor, and between these two a depletion layer will be there, where n-type semiconductor consisting of the positive, electrons as well as these things, and the depletion zone, and p-type semiconductor things, and sonar, sun will provide certain amount of rays on the p-type semiconductor, so that the electrons will move from p to n. Okay, this movement is continuously happening. Okay, so as it is a closed path, so we are going to connect a load, a light or lamp or something, so that the electrons will flow in this direction. Again, it is moving. So it is gone continuously happening till the sun exists, right? So the same thing as the photoconductive. So conduction means resistance. Resistance is which opposes the flow of current. Conductance means which allows the current. It is the ability of the material which is going to allow the current. Nothing but as light, nothing but photo energy is falling on the material, so that it starts conducting. So that if photo energy is falling on the photoconductive elements, then automatically resistance will decrease. So that automatically, if the resistance is inversely proportional to the conductance, right? So just observe, there is a power source will be there. Whenever the light rays are falling on this material, then automatically it is going to produce the nothing but the resistance is going to be reduced. So resistance, as the resistance reduces, the conductance will improve, so that the current conduction or the flowing of current will change. Just observe, this is the available in the markets. Okay, so these two terminals, between these two terminals, what we can have? Okay, so between these two terminals, we can observe the voltage or resistance to measure the conductance value. Okay, so these are the conductive materials which are there on the these things, and these two are the electrodes what we can have. and between the two electrodes. Okay, so photoconductive material will be placed as a track. So why we are going to make as like this means, as spiral means, in order to get the fuse length, just observe the spring. What is the actual length of the spring? It might be very high, but in order to keep that entire spring within a short space, we have to make it as spiral. Okay, here also we are making as like this. So terminals will be as of like that. So that if you start opening this, so it is of fuse in length, right? So as the photoconductive transducers of the device that changes their conductance based on the radiant flux hits them. Nothing but based on the radiance falling on the photoconductive materials, right? So that the resistance is going to be reduced. So photoconductivity is an optical and electrical phenomena that occurs when the material becomes more electrically conductive after absorbing electromagnetic radiation which are produced from the solar energy. So photoconductive, photo means solar, nothing but sun. Conductive means conductance. As the light falls on the photoconductive devices, the conduction will increase, nothing but the passing of current, nothing but distance is going to be reduced and passing of current will gets increased. Okay, so this radiation can be a visible light, infrared light, ultraviolet, or gamma radiation. For all these kind of input lights, it is going to be performed, nothing but it is going to respond, right? So we are having very huge applications for photoconductive transducers. Few of the things what I will just here. So relay control circuits, there we can have burglar alarms, light controlled switches, measuring attenuation of lights, counting number of packages moving on conveyor belts, etc., etc. So these are all the various applications where we can use the photoconductive or elements or transducers, right? Now coming to the resistive transducers. So resistive transducers are nothing but whose resistance are going to be changed by changing the sudden input phenomena. Nothing but if any physical parameter. So A is going to be converted into B, where B is resistance. So A will be any of the parameter. So it is going to convert into change in resistance. It is going to convert in change in resistance, right? That we'll see. So resistance of a metal conductor is expressed by simple equation, that is R equal to rho L by A. It's a well-known expression. Or resistance of the conductor in terms of ohms, L is the length of the conductor, A is the cross-sectional area, and rho is the resistivity of the material. So here the resistivity of the material depends upon what kind of material you are choosing. Okay, if you are choosing iron, so iron resistivity will be some other value. If you are choosing uh, nickel, nickel resistivity will be some other. If you are choosing tungsten, it will be having certain, nothing but the rho value depends upon what type of material you are choosing. So once the material is chosen, resistivity will be fixed. So in the మనం capacitance discuss చేసేటప్పుడు పాయింట్ చెప్పారు, capacitance C equal to epsilon A by D, where epsilon is the dielectric material and its properties, let it be. A is the area of cross section, D is the distance. So here also R equal to rho L by A, where rho is the resistivity, depends upon the material, L is the length, and A is the cross section area. Okay, in case of resistance we are saying resistivity, in case of capacitor we are saying dielectric material, right? So by changing, okay, rho L A, you can change rho, nothing but by changing the material we can change the resistance value. By changing the length we can change the resistance value. By changing the cross sectional area we can change the resistance value. So these are the three parameters which are going to influence the change of resistance value. So the resistive transducer is nothing but the device which is going to convert the input parameter into change in resistance. So while changing resistance, either resistivity of the material has to change, either length has to be changed, or either cross sectional area has to be changed, right? we'll see. There are different types of resistive transducers are there. Okay. First one is the potentiometer. Second one is the resistance pressure transducer. Next one is resistance position transducer. Next is strain gauge, thermistor, and resistance thermometer. So potentiometer or pressure transducer, position transducer, strain gauge, thermistor, and thermometer, resistance thermo or TD. So these are the various types of resistive transducers. Okay. Anyhow, with this we can stop this class, and tomorrow we'll get in detail about resistive transducers, right? Because why I am disconnecting here means in order to make inductive transducer, capacitive transducer, we have covered today. Resistive transducer will cover tomorrow, because we need to upload these files to the web. It needs certain space, right? So I hope today